anti-lock braking systems. Now, if you've ever owned a car, chances are you've heard of the term ABS before. But what exactly does this system do, and why do all modern vehicles have it? Well, first let's dive into a bit of history. The anti-lock braking system, also known as the ABS, used to be quite the luxury. Back in 1971, it was just another expensive optional standard to vehicles after being invented years before by a man named Mario Palizzetti. A couple more decades came by, and by the mid-90s, the early adaptations of ABS basically flooded the market and just became a standard on all passenger cars as well as light trucks. Since then, the ABS system has quite expanded, becoming more and more complex and eventually paving the path for electronic stability control, or ESC, as well as other safety-related features such as your electronic brake force distribution, traction control, hill assist, and everyone's favorite with the recent craze of self-driving vehicles, your adaptive cruise control. More regarding those safety features and stuff later on in the video. But what exactly does ABS do, and what's the point of even having it? Just to be clear, not everyone in this world wants to be a drift king running the mountains to deliver tofu every morning. Most people just want to go from point A to point B as safely and easily as possible. Well, as the name suggests, the ABS prevents your brakes from locking up by maintaining the highest possible coefficient of friction between your tires and the road surface while braking on panic conditions or on very slippery surfaces. The higher the coefficient of friction, the less time and distance you'll need to cover to come to a complete stop, and the lower chance of your vehicle skidding in general. If your wheels were to lock up, as I mentioned, you would most likely begin to skid. Now, this would often lead to two different kinds of conditions. First off, you would have either oversteer, a case where your rear wheels would lose traction, making you swing out to the left or to the right more than you intend with your steering input, or even worse, the second condition, understeer, which is when your front wheels lose traction, making it practically impossible to steer left or right. At that point, you better just hope you're not nearing a sharp turn on a mountain, or else you'll be off the cliff in no time.
To get a better understanding on ABS, first we have to learn some basic fundamentals such as pressure modulation, slip rate, and how the brake pedal feels itself. At the point when the driver rapidly or solidly applies the brake and holds the pedal down, the brakes of a vehicle not outfitted with ABS will nearly immediately lock the wheels. The vehicle slides as opposed to rolls to a stop. During this time, the driver likewise has a truly challenging time monitoring the vehicle, and the vehicle can slip crazy. The sliding and the absence of control was brought about by the locking of the wheels. In the event that the driver had the option to deliver the brake pedal not long before the wheels secured and afterward reapplied the brakes, the sliding could be prevented. At the point when the brake pedal is siphoned or beat, pressure is immediately applied and delivered at the wheels. Pressure adjustment attempts to forestall wheel locking. Automated stopping device frameworks can adjust the strain to the brakes as frequently as 20 times each second. This is known as pressure modulation. By tweaking the strain to the brakes, grating between the tires and the street is kept up with, and the vehicle can reach a controllable stop. Since the ABS is now controlling framework pressure, most present-day frameworks have some control over the water-driven strain to the wheel brakes instead of metering and proportioning valves utilized on non-ABS frameworks. Electronic brake force distribution is utilized to keep up with balance between the front and back brakes by observing the back tire speeds during slowing down. In the event that the back tires delay down more rapidly than the front wheels, the ABS can restrict strain to the back while permitting strain to the front brakes to work depending on the situation. The possibly time-diminished grading guides in slowing down is the point at which a tire is in snow or on free rock. A locked tire permits a little wedge of snow or rock to develop in front of it, which permits it to stop in a more limited distance than a moving tire. Controlling is another significant thought. Up to a tire doesn't slip, it heads just in the frame of mind in which it is turned. One of the enormous benefits of ABS, accordingly, is the capacity to hold control of the vehicle under all circumstances. Now that we know about pressure modulation, what about slip rate? The mobility of the vehicle is diminished assuming the front wheels are locked, and the strength of the vehicle is decreased in the event that the back tires are locked. Anti-lock slowing mechanism unequivocally control the slip pace of the wheels to guarantee most extreme hold force from the tires. and it accordingly guarantees the mobility and soundness of the vehicle. An ABS control module works out the slip pace of the wheels in light of the vehicle speed and the speed of the wheels, and afterward, it controls the brake liquid strain to accomplish the objective slip rate. Despite the fact that ABS forestall total wheel secure, it permits some wheel slip to accomplish the best slowing down conceivable. During ABS activity, the objective slip rate can be from 10 to 40%. Zero slip implies the wheel is rolling uninhibitedly, though 100% means the wheel is completely locked. A slip pace of 25% means the speed of a wheel is 25%. Not exactly that of a free-moving wheel at a similar vehicle speed. Numerous things are thought about while deciding the objective slip rate for a specific vehicle. As far as some might be concerned, the range is exceptionally low, 5 to 10%, and on others, it is high, 20 to 30%. But how does it actually feel on your foot if ABS turns on during a panic stop? The brake pedal on the vehicle outfitted with ABS has an expected vibe in comparison of an ordinary slowing mechanism. At the point when the ABS is initiated, a little knock followed by fast pedal throbs will go on until the vehicle halts or the ABS switches off. These throbs are the after effect of the tweak of strain to the brakes and are felt more on certain frameworks than the others. This is because of the utilization of dampening valves in some adjustment units. In the event that pedal feel is of worry during conclusion of a brake issue, contrast the brake pedal feel and that of a comparable vehicle with a typical working, non-freezing stopping device framework. With ABS, the brake pedal exertion and pedal feel during an ordinary slowing down are like that of a regular power stopping mechanism.
ABS has many hydraulic components involved, one of them being the accumulator, which is used to store hydraulic fluid to maintain high pressure in the brake system and to provide residual pressure for power-assisted braking. Normally, the accumulator is charged with nitrogen gas and is an integral part of the modulator unit. This unit is typically found on vehicles with a hydraulic assisted brake system. Full charge can reach 2700 psi. It also has an anti-lock hydraulic control valve assembly. This assembly controls the release and application of brake system pressure to the wheel brake assemblies. It may be of the integral type, meaning this unit is combined with the power boost and master cylinder units into one assembly. The non-integral type is mounted externally from the master cylinder power booster unit and is located between the master cylinder and wheel brake assemblies. Both types generally contain solenoid valves that control the releasing, the holding, and the applying. It also includes a booster pump, which is an assembly of an electric motor and pump. The booster pump is used to provide pressurized hydraulic fluid for the ABS. The pump's motor is controlled by the system's control unit. The booster pump is also called the electric pump and motor assembly. The ABS also includes a booster master cylinder assembly. The booster master cylinder assembly, sometimes referred to as the hydraulic unit, contains the valves and pistons needed to modulate hydraulic pressure in the wheels circuit during ABS operation. Power brake assisted is provided by pressurized brake fluid supplied by a hydraulic pump. It also has a fluid accumulator. Different than a pressure accumulator, fluid accumulators temporarily store brake fluid removed from the wheel brake units during the ABS cycle. This fluid is then used by the pump to build pressure for the brake hydraulic system. There are normally two fluid accumulators in the hydraulic control unit, one each for the primary and secondary hydraulic circuits. The ABS system includes a hydraulic control unit. This assembly contains the solenoid valves, fluid accumulators, pump, and electric motor. This is actually a combination unit of many individual components found separately in some systems. The unit may have one pump and one motor, or it will have one motor and two pumps. One pump for half of the hydraulic system and the other for the other half. The ABS has a main valve. This two-position valve is controlled by the ABS control module and is open only in the ABS mode. When open, pressurized brakes fluid from the booster circuit is directed into the master cylinder circuits to prevent excessive pedal travel. The ABS system comes with a modulator unit. The modulator unit controls the flow of pressurized brake fluid to the individual wheel circuits. Normally, the modulator is made up of solenoids that open and close valves. Several valves that control the flow of fluid to the wheel brake units and electric relays that activate or deactivate solenoids through commands of the control module. This unit may also be called the hydraulic actuator, hydraulic power unit, or the electrohydraulic control valve. The solenoid valves are located in the modulator unit and are electrically operated by signals from the control module. The control module switches the solenoids on or off to increase, decrease, or maintain the hydraulic pressure to the individual wheel units. The ABS also has a valve block assembly, which attaches to the side of the booster master cylinder and contains the hydraulic wheel circuit solenoid valves. The control module controls the position of these solenoid valves. The valve block is serviceable separate from the booster master cylinder, but should not be disassembled. An electrical connector links the valve block to the ABS control module. Last but not least, the ABS has wheel circuit valves. 2 solenoid valves are used to control each circuit or channel. One controls the inlet valve of the circuit, the other controls the outlet valve. When inlet and outlet valves of a circuit are used in combination, pressure can be increased, decreased, or held steady in the circuit. The position of each valve is determined by the control module. Outlet valves are normally closed and inlet valves are normally open. Valves are activated when the ABS control module switches 12 volts to the circuit solenoids. During normal driving, the circuits are not activated.
In the electrical system, the ABS control module is a small device found on the master cylinder. It monitors how the system works and controls the anti-lock system. The module relies on inputs from the wheel speed sensors and feedback from the hydraulic system and make sure it's working correctly. As for the control module, it translates the signal into wheel speed. The sensor is normally a small coil of wire with a permanent magnet in its center. The data link connector or the DLC provides the information needed for the vehicle to work, for example operating conditions and diagnostic. The anti-lock brake pedal position sensor or the BPP sensor is used to tell how much the pedal is depressed inside the ABS module. It is located by the brake pedal on the floor of the car, and the indicator lights is in the majority of our cars with ABS nowadays. One of the light works with the ABS and the other is with the base brake system, which that one is red, for example when brake fluid is low or a problem in the brake system itself, or the parking brake is on. The amber light is for the ABS unit. Both of the lights will turn on if there is a big problem in the system. The yaw sensor. Its job is to monitor the sideward movement, forward and rearward movement, and the movement around the center of the vehicle's axis. They are put into place to ensure the proper braking during turns and to keep the vehicle stable in corners. The pressure switch grounds the pump motor relay coil circuit, activating the pump when accumulator pressure drops below 2030 psi. The switch cuts off the motor when pressure reaches 2610 psi. It also can turn on indicator light if it drops below 1500 psi. The pressure differential switch is found in the modular unit. It sends a signal when there's an undesirable difference in the hydraulic pressure. Relays are electromagnetic devices used to control high current circuits with low current circuits. In the ABS system, the relays are used to switch motors and solenoids. A low current signal from the control module energizes the relays. The toothed ring, also called tone or reluctor ring, found on the axle shaft, differential gear, and the wheel hub. Used with the wheel speed sensor, the number of teeth around it amount can vary depending on the manufacturer. As the ring rotates, each tooth passes by the wheel speed sensor. An AC voltage signal is generated between the sensor and the tooth. As the tooth moves away and breaks the signal, turning it into a pulsating ring. The wheel speed sensor is mounted near the toothed ring. There are 2 types of sensors that are in use: passive sensors, which generate AC voltage signals, and active sensors, which generate digital DC signals. Active sensors have 2 or 3 wires on either Hall effect or magnetoresistive sensors that produce a square wave digital signal. Active sensors are most common now because digital sensors can be down to 0 miles per hour and can tell us the direction where the wheel is turning. The magnetic resistance of the magnetic circuit is changed, resulting in the induction potential in the coil. This is called magnetic induction.
Non-integrals controls and calculates the slip rate of the wheel and also controls the brake fluid pressure that targets the slip rate. If the module senses that the wheel is about to lock on the input sensor, it will pulse and open the inlet solenoid valve that is usually closed to help prevent fluids from entering the circuit. This will help dump any pressure that is trapped between the closed inlet valves and goes back to the master cylinder reservoir. When the affected wheels return to normal speed as seen with the others wheels, the control module returns valves to its normal condition for fluids to flow to the affected brakes. Integral brakes are applied in normal conditions. The pedal actuates a push rod. It operates a lever that moves the spool valve. When the spool valve moves, it closes the port from the accumulator to pressure on the brake pedals. For this to allow hydraulic fluid under pressure from the accumulator to enter the booster chamber, as hydraulics pressure enters, it pushes the booster piston forward to assist mechanical thrust from the push rod.
The ABS system can come in multiple kinds of types depending on the amount of wheel speed sensors there is. First off, we have one channel, which would have one single sensor, typically found on the rear axle, and is used to measure the speed of the driving wheels. A single valve would also regulate both the rear wheels and operate as soon as the wheel speed sensors predict that the wheels are about to lock up. However, since it does only contain one single valve to do all the work, you can't really rely on it too much to distribute effective braking force. Next in line would be a two-channel system. Now, these types of systems are basically obsolete now, however, at one point they did definitely exist. Essentially, these came with 4 wheel speed sensors, so one sensor on each wheel, and if those sensors were to detect some kind of lockup, then 2 valves would act to stop all 4 wheels equally. So basically you have one valve connected to the front wheels and one to the rear. However, the one downside to this, similar to a single channel system, is that it also can't quite distribute that braking force evenly or effectively, nor even accurately to all 4 wheels. After that, now we move on to 3-channel systems. Now, there's 2 different kinds of 3-channel systems, and they include either 3 wheel speed sensors, or if not, 4 wheel speed sensors. The 3-wheel sensor setup is quite prevalent, especially in most 4-wheel drive pickup trucks nowadays, and with this system, the front wheels would each have a valve and a sensor, whilst the rear wheels would only share one sensor and one valve. This does make sense, however, since due to weight transfer, the majority of the vehicle force would go towards the front of the vehicle during braking, therefore making it a lot more effective in terms of predicting when your wheels would lock up, unless of course you decided you only want to drive in reverse for the rest of your life. As for the 4-sensor counterpart of a 3-channel system, it essentially just includes an extra wheel speed sensor, this time being on both rear wheels. However, both those rear wheels do still share the same valve, so when one wheel decides to lock up, both would essentially get affected by your ABS, trying to reduce the amount of brake pressure going to both wheels. Last but not least, we have the 4-channel systems. Now, this is what's commonly found on most modern day vehicles nowadays, and in this case, each wheel would essentially have its own valve as well as its own wheel speed sensor, making the most out of braking force as well as being the most accurate in terms of predicting each wheel so you never go into any kind of skidding motion ever again. Now, as I mentioned earlier in the beginning of this video, the ABS system is quite expanded, becoming more and more complex each year. This is when we get into things such as your traction control as well as electronic stability control, also known as your ESC. First off, in our list of modern day applications, we have your adaptive braking. In today's market, we have a lot of automobiles equipped with electronic brake assist systems that can prepare or apply the brakes based on the operating conditions. For example, some cars can apply the brakes ever so slightly when driving in wet conditions to keep the pads and the rotors dry for maximum responsiveness. A lot of systems nowadays can also determine if you're in a situation where you're engaging in an emergency stop. Now, this can be done with the use of forward-facing cameras as well as radar signals from the adaptive cruise control system. These forward-facing detection systems basically determine if an obstacle is in the path of the vehicle, and if someone or something were to enter its path, it would immediately alert the driver, and if the driver doesn't apply the brakes, the car will try to stop on its own. With adaptive cruise control, it's basically a similar story, however this time, it uses the ABS system to apply your brakes as needed to maintain a set distance between you and a moving vehicle ahead of you. Next in line, you have your automatic traction control, also known as your ATC. This system essentially applies the brakes when a drive wheel attempts to spin or lose traction. Controlling wheel spin is the goal of both the ABS and the ATC combined. ABS just controls what's known as negative wheel slip, which is when a wheel is going slower than intended or slower than all the other 3 or 2 wheels or however much wheels are spinning out, and this is done by releasing some of the hydraulic pressure on the wheels. Meanwhile, your ATC controls what's known as positive wheel spin, or well, basically when a wheel is going faster than intended. This as a result adds hydraulic pressure in order to slow down that wheel that would be spinning too fast. Last but not least, we have your stability control, which is either known as your ASC or ESC. This system prevents skids, swerves, or even rollover accidents. Basically, the system applies the brakes at one or more wheels in order to give you some room to correct the steering. However, do keep in mind that the ESC does not overrule the laws of physics. It can't do anything about the physical limits of your vehicle, nor can it increase traction. It's simply there just to help you regain control of your car, not prevent losing control in the first place. At the end of the day, the car's tendency to roll is mostly influenced by its height, track width, as well as its suspension stiffness. So, what exactly do we get out of this video? Well, as a conclusion, your ABS system is pretty much integral if you want to talk about safety. Not only that, but it's what allowed us to have some pretty cool advancements. Only time will tell what else will be implemented in the future, but for sure for technicians it's just gonna get more and more complex than it already is. But hey, that goes for just about everything.